This video is going to take us through a quick tour of section 15.1, the concept of probability distributions. In chapter 9, we work with random variables, and we said a random variable is a variable that can take on any series of values depending upon the random outcome or the chance outcome of some type of event or experiment. And for our purposes, we're just going to say that random variables will take on numerical values. In this chapter, for sure, no categorical variables. Everything is going to be quantitative and specifically numerical values. And we're going to see in this unit that we can run across two types of quantitative, numerical, random variables. Those are discrete, ones that we can count, typically as integers, or continuous random variables that can take on any of an infinite number of values within a given interval. And we'll work with two types of distributions, one for each of those different types. For discrete random variables, we're going to talk about something called the binomial distribution. For continuous random variables, we're going to talk about the good old normal distribution, what we've called the bell curve that you might be familiar with. Now, we did a lot of work in chapter 9 with, we'd have a value that our random variable could take on, a set of values that our random variable could take on. We'd build some cumulative frequency and cumulative relative frequency tables. And by the way, those things translated into, with those particularly the frequency tables, translated into how frequently a given value occurred for a particular random variable. We might have said of our random variable x, 5 times we had a value of 2. 7 times we had a value of 3, so on and so forth. And then when we knew all the number of total observations that we had, we divide and we come up with the percentage for each, the relative percentage for each of those different variables. And we're going to do something just like that with random variables here and build what is called a probability distribution. So let's do it with a couple examples. And we're going to start with a classic example, and that is you roll 2 dice and you find the sum of the values that show up on the dice. Now, both of these dice are 6-sided, so each dice can have a 1, 2, 3, 4, 5, or 6. And so if I did this, and we did this in class actually, 1, 2, 3, 4, 5, 6, I drew going down, and I drew 1, 2, 3, 4, 5, 6 going across. We came up with 36 possible values that could come off, and we then filled in the table. You know, a 1 and 1 would give us a 2. A 6 and 6 way down there gave a 12. And so the random variable x is just the sum of those 2 dice. It's a discrete random variable. We could only get so many values. We could get values from 2, a 1, 1, double ones, all the way up to the highest sum that we could ever get is a 12, a 6 and a 6. And so 2 through 12 are all the values that our random variable could take on. And if we did a little work, if we built this whole table out like we did in class, and you can do yourself if you weren't in class to watch this part, is you can build a very quick probability distribution. There was only one option where you could get a 2, double ones. There was only a way in which you could get a 12. That would be the 6 and 6 way down there. And if you kept doing all the work, what you would see is, hey, 2 out of 36, a 2 and a 1, or a 1 and a 2 could produce a sum of 3. So on and so forth. So if you look, you can see the probability distribution function for the random variable x, which represents the sum that you get when you roll 2 dice. And I kept everything over 36 here. And this is a great probability distribution function. It's good in that it covers all our possible random values of x. By the way, if you add all these individual probabilities up, they're going to sum to 1. On this probability distribution function, you notice how we have bars that are separated in each random variable. Why do we do that? Well, it's because these are all mutually exclusive. There's no way you can have a sum that is both a 2 and a 3 when you look at a pair of dice. Each one of these is mutually exclusive. And so there's a whole bunch of things that come out of a probability distribution table like this, and they're going to be summarized on your next page. For any value x, any of your random variables that fits in your sample space, discrete random variable x and all the values that could come up, the probability of that event happening, your random value taking on a specific value of x, is always between 0 and 1 inclusive. The individual probabilities of all the possible values of x, your discrete random variable, are going to sum to 1, as we said before. And if we ask you to find the probability that the random variable takes on a range of a certain interval, maybe like, hey, what's the probability that your dice roll is from 4 through 6? Well, we could just add up the individual probabilities, the probability of getting a 4, plus probability of a 5, plus probability of a 6, and answer a type of question of that nature. So let's do one more example very quickly. Here's a bar graph that you're given. That looks like a frequency distribution if you think about it. And these are letter grades. An F, 0. These are quality points, for like a GPA. A grade of D gets 1 quality point, a C, 2, a B, 3, and an A, 4. And if you work here real quickly, well, what can we see? Random variable X is just a value 0, 1, 2, 3, or 4. Mutually exclusive again. And it represents the letter grade that you happen to get. If I want to create a PDF, well, what can I do? I can put a 0, 1, 2, 3, and 4, just like I did right down here at the bottom of our table. And what can I do? Well, 4 Ds, 5 Cs, 9 Bs, 9 As. If I add that all together, there are 27 students in this grade analysis. Probability of 0, well, there's nobody, 0 out of 27. There's 4 people who got a D, 4 out of 27, my random variable taken on a 1. 5 27ths for the C's, 9 27ths, 9 out of 27 for the B's, and 9 27ths for the A's. What's the probability that this randomly chosen student receives a B or better? Well, a B or better is a random variable value of 3 or 4. That probability is nothing more than 9 27ths plus 9 27ths, or 8 27ths. So there's a tremendous amount of power in these probability distribution functions, but there's some very important statistics that we can take out of them as well. And those are going to be the expected value, which also translates to the population mean for our random variable X, and also 2 other concepts that work with measuring spread of our random variable, and that'll be the variance and the standard deviation. So we'll start working with some of those. And I'm just going to move directly into our little analysis model that we put here. I asked you, this was before we even talked about what expected value is. I said, you have a chance to play a game where you pull a marble from a container. You're told the chances that the marble is blue is 10%. And if your blue marble is pulled out, you're going to receive $8. If the marble isn't blue, you need to pay $1. Would you play this game? Well, you're going to play this game, one. Well, we can assume that the only reason you would want to play is because you'd like to come out ahead from a money standpoint. And so if we look at this, well, what would I think? Well, 9/10 of the time, I'm going to do what? Lose $1. 1/10 of the time, I'll get $8. Another way to look at this is say, well, let's pretend that I decide to play this game 10 times. Well, it sounds like 9 out of 10 times I would lose $1. I'd be down $9. On that 10th time, I'd get $8. Gee whiz, I still have a net loss over those 10 games of $1. And if I just said, hey, what's the chances of just playing one game? Well, what would I find? My expected value, what I expect is, hey, if I lose $1 over 10 games, over each game, I would expect that, hey, my losses are going to average out to 10 cents. Would I want to play this game? The answer is absolutely not. And it's because we've calculated something called an expected value. This is a good PDF for that scenario. 2 values at my random variable, which is actually how much money I win when I play the game. I can either lose $1 or I can win $8. 90% of the time, 9 out of 10, I'm going to lose $1. I'll get those $8 only 1 out of 10 times. And if I do a weighted average of this, I'll actually go ahead and get a negative 10 cents, a loss of 10 cents. I'm certainly not going to play that game. Now, if I had changed this, if I said, hey, if the blue marble was worth $10, would I play this game? In that case, yes, I would. I'd lose $1 9 out of 10 times. I'd be down $9. On my 10th time, what would I get? I'd get $10. Well, after 10 plays, theoretically, I'm going to be, what, $1 ahead. I would want to play this game. And this all translates into the concept of expected value. And we could do an expected value for our little distribution, well, not our little, but our pretty big distribution we did here, the die roll, and say, well, what do we expect we would get? And if you looked at the weighted average video already, what you see from the book as a definition of what an expected value, it's the mean. You see this Greek mu here. You also see it written as capital E of x. That's the expected value of our random variable x. What is it? Well, it's a sum of what? The particular values that our random variable can take multiplied by the respective probability of that particular random variable value. And if we do this across all values of our random variable, multiply by each of their individual probabilities and add them all up, we get the expected value. Now, it's also referred to in this case as our population mean. You also see that good little Greek letter mu being written for your expected value. If we happen to do that for our little PDF here, I'd do 2 times 1, 6, plus 3 times 2, 36, so on and so forth, plus 11 times 2, 36, plus 12 times 1, 36. And in class we did this, but if you do it with your calculator, you'll wind up getting 252 over 36, which will actually turn out to be 7. So in general, if I played this game over and over again, what do I think, what do I expect is going to be my average dice roll value? It turns out to be 7. That's what I expect to happen. Now in this one particular instance, for this example, it turns out, well, 7 is also the item that has the highest probability. It was a question that was asked in class, and there's a couple key pieces. Your expected value is not necessarily the most likely value. The way this particular example, if you look at it, it is it is perfectly symmetrical. And so there is symmetry around that value. And in this case, because of the special characteristics of this little PDF, it turns out that our expected value also matched the high value. But that's usually not something that is going to happen. Usually the numbers are going to work out in some type of different fashion. But just recall your expected value. This is how you'll compute it at all times. So let's do one more example very quick. The number of accidents on the New Jersey Turnpike during the Friday rush hour is going to either be 0, 1, 2, or 3 accidents on a Friday rush hour. Probabilities of each of those values is 93% for 0, 2% for 1 crash, 3% for 2 crashes, 2% for 3 crashes. What's the expected number of accidents during rush hour? Well, that would be 0.93 times 0 plus 0.02 times 1 plus 0.03 times 2 plus our last probability, 0.02 times 3. If we do the work here real quick, I'm going to have a 0.02 plus a 0.06 plus a 0.06. How many accidents do I expect? I expect 0.14 accidents on the New Jersey Turnpike during rush hour on a Friday. So quickly, what can you see? 0.14, it certainly isn't one of those random variable values. It is, again, it is a weighted average of the random variables in our PDF and their associated individual probabilities. Now, we also have talked about concept of variance and standard deviation. When we used to do our variance, what did we say it was? Well, it was the sum of the squared distances from the mean and the average of that. So if we had n observations, we took each individual observation, x sub 1 through x sub n. We subtracted them from their mean. We know how to compute the mean of our variable. We square that, sum them all up, and divide by n. And that gives us the standard deviation, the variance. And how do you get the standard deviation? Well, next page will show that. Standard deviation is nothing more than the square root, the positive square root of the variance. So just like expected value, we do what? We take each individual random variable, multiply it by its probability to get our weighted average, our expected value. To come up with our variance, it's a similar weighted concept. We take each individual observation, subtract it from its mean, its standard deviation, its mean, its expected value here, that mu, square it, and we multiply each of these by their respective probabilities. That's computing a weighted average. Again, you can watch the weighted average concept video if you need a little bit more of a refresher in that. But I think, particularly as you do the reading through this chapter, I think most of this will kind of fall into your laps relatively easily. Now, the last thing to finish up with this particular lesson is I'm going to take one example. We're going to go ahead and we're going to build from a PDF. This is a random variable out here. It's the number of liters of milk consumed by somebody or some family or whatever. I'm not even worried about that, but it's a discrete random variable. 0 liters consumed 8% of the time, 1 liter 20%, so on and so forth. I can compute an expected value very, very quickly. Here's my random variables, just the table. All I've done is I've turned it around and I've written the random variable value and their associated probabilities. And in my next column, all I've done is I've taken this value and multiplied it by the one right next to it. So 0 times 0.08 gives me 0. 1 times 0.2, 0.2. 2 times 0.36. You don't need me to read the rest of them. But I get all these values and I sum them across and I get 2.2. So on average, if I did this over and over, measured week after week after week, what would I expect? I would expect that I consume 2.2 liters of milk. Now, the variance, well, what would that have me do? Well, here's the beginning of your table. I, again, have all the same values. There's my different values of the random variable. Here is my probability that I take on those values. What did I do next? For each of these values, I did the value of x minus mu, minus 2.20. So 0 minus 2.20, negative 2.2. 1 minus 2.2, negative 1.2. So on and so forth in this first column. What did I do next? I took this column and I squared it. So negative 2.2, when I square it, I get 4.84. Again, remember, these are what? Weighted averages. So what will I next do? I'm going to take this squared value, 4.84. I'm going to multiply it by 0.08, and I'll get 0.3872. I'll continue to do this same thing. This column times this column, so to speak, column 3 times column 2, and I'm going to put that value into my column 5. And if I take all these values, again, you can see it in the book, you can do it yourself. It's probably not a bad idea to manually compute these one times. I find out that the variance of my random variable is 1.52. 1.52 liters, I guess, is what the unit of measure here would be, units squared. Can I compute a standard deviation for this particular probability distribution? I sure can. What do? Take the variance and take the square root of it. The square root of 1.52 is 1.23. So this is the introduction to chapter 15 with section 15.1. Make sure you're very comfortable with the weighted average concept, understand the key elements of a probability distribution function, and if you can work from these, you'll be off to a very good start for this unit.